first talk is from Professor ZhiXun Shen, and he will tell us about their newest work on electron-doped Cuprates, unveiling surprises and insights into persistent challenges in high-temperature superconductors.
Great. Thank you very much for inviting me. For me to have an opportunity to share with you some of our most recent work on the electron-doped Cuprates. It turns out that the little cousin of the Cuprates on the electron side can tell us, reveal a number of surprises, and it can tell us some of the persistent challenges in the Cuprate. Let me start out by acknowledging the collaborators. This is really a collaboration between Standford SLAC, KTH, and also the theory group, both locally and also that of Berkeley and Leiden. This is also in memory of young Zhi-Xun, who passed away recently. Such an extraordinarily talented scientist and in so many dimensions. So the samples were grown in early part of the sample were grown by with Yang Li's collaboration. Let me highlight particular the contribution of graduate student Keijun Xu and also staff scientist Makoto Hashimoto in this work. Okay. So this is the old subject of the Cuprates, and much of the effort being on the whole doped side. TC is higher and a lot. But generally, this is a single layer system, and you have the couple oxygen plane as shown in this case, and also have the charge reservoir holding in charges in the system. Compared with the other systems, the Cuprates are one thing coming out. It's simultaneously so simple. It's a single band problem, so it's very simple. And you can see if you compare with the other compounds such as iron pnictides, you can clearly see it's much simpler in terms of band structure. I took this from her used drawing, and yet it's just as rich in terms of physics. So that's what I hope to get to it today. And now, since my talk follows earlier session by Peter Johnson, and so I don't need to make another introduction of angle-resolved photoemission spectroscopy, and that's the technique we will use to study. Okay. So among the Cuprate problem, there are a few things which we all agree today. One of them is the D-wave superconductivity. Here is the map of the D-wave gap along the underlying Fermi surface, and the dot are the data, and you can see the solid line is the D-wave gap form. Then there's this one we have a consensus, but there's another issue is so-called pseudo gap. This has been around for almost 3 decades, is one of the persistent challenges in the Cuprate research. Fermi surface is a topological concept, namely the volume enclosed by the Fermi surface tells you the number of carriers in the system. Okay, but early on, almost 3 decades ago, it's found that sort of the Fermi surface stopped in the middle of nowhere. And since this is a volume concept, it cannot stop in the middle of nowhere. So one can think about the yellow section region being gapped. And this is one of the persistent questions of the field. Now, it's a common phenomenon. For example, you see it in CCOC, you see it in the BISCO underdoped BISCO single layer, double layer system. So this is generic features in the Cuprate problem. Now, these are many ideas for what's the origin of pseudo gap. One, the preformed pairs. One's competing order. It could be magnetic scattering coming at the hotspot. The complications for p-type is that it happens near the Briand zone. Let me see whether I can have a laser pointer. Okay, near the Briand zone boundary in this region. If you can see my laser pointer. Okay, Then there are many complications. There's one hole singularity, which distorts things. And we also know that there's anti-ferromagnetic scattering. That's the anti-ferromagnetic hotspot. Then there's also known that there's electron-phonon coupling can be preferentially strong at antinode. So there were a lot of debate on this issue. Okay. So recently we worked on the other side. As I said, much of the effort is on the hole doped, and we work on the electron-doped system. Okay, and I'm going to talk about two subjects. One is the faint Gossamer Fermi surface and the unexpected pairing mechanism along the Gossamer Fermi surface. The other is another thing, which is the most recent work to show that this large range of the long-range ordered magnetic states actually has a hidden Cooper pairs in this problem. So these are the two things I hope to address. Okay. Now, for the first subject, let me going to tell you what I'm going to tell you, then I will then develop this subject. Take a piece of Fermi surface like this, okay? Now you fold it around the anti-ferromagnetic zone boundary and look like this. Then you reconstruct the Fermi surface. You go from this picture to this picture, okay? Normally, you say, okay, if I have a starting point like this, if I will further develop a superconductivity, you would think that superconductivity should happen on top of the reconstructed Fermi surface. Indeed, in CDW systems like such as niobium diselenide, the superconductivity happened on the reconstructed Fermi surface. Okay. What I'm going to tell you is that in this case, actually the superconductivity, the maximum superconductivity, happen in a region that's the maximum gap. Maximum superconductivity happens in the hotspot. Note that there's another piece of Fermi surface inside here, which I put a dashed line. This one depends on specific doping. It could be a Fermi surface, or this piece could be below the Fermi surface. Okay, but the antinode piece is the most robust. Okay, now this kind of Fermi surface reconstruction is known in the field for a long time. You start out with the Fermi surface, the reconstructed one, then you have the hotspot emerges with doping, and eventually you become a large volume Fermi surface. Okay, then you can also, this is also seen by transport, and you can see there's a sudden change of transport property of the carriers consistent with the jump from smaller pocket to large Fermi surface. And this sort of behavior in angle resolved formation is already there in very early on in Peter Armitage's thesis, and also Matsuya or show additional development in this. But overall, it's a very clear picture. The dominating one with the antinodal pocket, depending on your doping, you can see the emergence of this piece of Fermi surface, and connecting these two, that's the famous anti-ferromagnetic hotspot. That is the spot the unreconstructed Fermi surface cross the anti-ferromagnetic zone boundary. Okay, so you can see from underdoped one to overdoped system. Now, more recently, we start to look at this problem again, and in this system, actually, we begin to see the other side of the Fermi surface, and you can see that you see the folded band of the pin. So that's sort of a complete Fermi surface, and you also can see the small pocket when it's doped enough, and you can benchmark the volume of this small Fermi surface together with the quantum oscillation. They agree quantitatively. So in that sense, we have a pretty good idea of what the Fermi surface looks like in those systems. Okay, now let's come to the interesting problem. The issue, if you want to make a pure electronic pairing in a single band system, you have the dilemma. The same electrons have to do two competing things, to pair and to be paired. Okay, this was pointed out very early on by Bob Schrieffer, that if you do these two things, the process of pairing by those same electrons will modify its band structure, eventually will cancel things out. So this is sort of, that's why it's always a question how the system will behave. Okay. So again, I'm going to tell you what I'm going to tell you. It basically to say that if I would measure the gap along the underlying Fermi surface, naively, I would say the gap should be maximum along this Fermi surface. And as you can see, which I'll show you, that the maximum now is not along this Fermi surface. It's a gap, there's a superconductivity, but maximum is where there's no reconstructed Fermi surface. Okay. This clearly, as you will see, also ties into the mystery of the pseudogap. This non-monotonic behavior of the gap is also seen early on. It's sort of seen in particular in Sato and Matsui's paper, and it's consistent with the earlier work by Peter Armitage. So what we see here is consistent with the earlier work. Okay. However, in none of the earlier work, you were able to see the superconducting coherence peak. So there's always a concern that this profile of the gap, which you'll see is consistent with the pseudogap, can be confused as being the residual of the pseudogap because it's not clear you can prove this is superconductivity. Okay, and that's the some of the recent data. As you can see that if I go cut around 1, 2, 3, 4, 5. You can see around 1, you can see the band bends back, enter the near the Fermi level, bends back around the anti-ferromagnetic zone boundary. As you go from 1 to 2, this magnetic fold band, folded gap gets bigger and bigger, okay? And by the time it cuts number 5, that's where the hotspot is. You can see that this main feature being gapped dramatically. That's sort of this kind of band, the red feature. Okay. Then when you cut number 6, the antinode, you can see that again, you see a very strong band, and this band gets close across the Fermi level. You can see there's a discontinuous jump between 5 and 6. Okay. Also, pay attention that you see states of 5. You see where my cursor is. Okay. Now this is well inside this magnetic gap, anti-ferromagnetic gap. Now, if seeing states inside the gap is not that surprising. In a gapped system, you often have impurities and all that. The question is that, are those interesting states? Okay. So here I'm showing you data. Okay, that's a sort of raw image of the data. And you can see as I move from here, nodal direction to antinodal direction, you see the spectra moving to higher and higher energy, and it reach a maximum at the anti-ferromagnetic hotspot. Okay, and this is the pseudogap phenomena, as you will see. Okay, that's where the gap is. I hope you also see that at the lower energy, there's also another feature following this way. And I'll prove to you this one turns on only below the superconducting transition temperature and is the Bogoliubov quasi-particle. Okay. And now let's take a piece of that. Okay. So this feature is the high energy feature. That's the high energy pseudogap. And this feature is this little blue peak. Okay. And you can see that it's not there above TC, but it's clearly identifiable below TC. Now we can do the detailed temperature dependence, and you can see that this quasi-particle peak, and they disappear at the superconducting transition. So this in-gap state is not some impurity state of the bare sample. Actually, is a state that gives rise to superconductivity. Okay. And you can see this gap turns on at the superconducting transition temperature. Okay, now we can come back to it. You can see that we have proven that actually those states, when you pull below TC, turn into an interesting superconductor. So there are two sectors of state. This is the main feature of the state. Then there's another sector, much weaker, but clearly there and active in superconductivity inside. Okay, so there's two sectors of the state. In that sense, I'm going to draw the Fermi surface. There's a piece which reconstructs the Fermi surface. That's the main piece. But then there is the faint piece as shown by these orange features, and that's the second piece. And we call that the gossamer Fermi surface, the faint gossamer ghost-like Fermi surface. Okay. Now let's look at the temperature dependence. Okay. Now the momentum dependent. I've shown you this peak showing up only below TC, and this peak now show a momentum dependence. If I plot the feature at the anti-node, you can see that the gap is smaller, the coherence peak is also smaller. On the other hand, when I plot the feature at the magnetic hotspot, you can see that the gap is bigger and also the coherence peak is bigger. Okay. So here where I plot, you can see as I go along from the Fermi surface here, you can see the big features show a maximum gap. That means that's where the pseudo gap is the largest. So this connects to earlier one. This is really the anti-ferromagnetic pseudo gap. It broadens the feature. Okay, and yet surprisingly, in other words, it damages all the low-lying states. And you need low-lying states for superconductivity. Okay, but in that sense, the pseudo gap is very bad for superconductivity. So the anti-ferromagnetism appear to be simultaneously doing bad things, also promoting good things. You can see the superconducting gap as above. So this is the dilemma I talked about earlier. How come the electrons can be so clever that simultaneously be good and bad? So come back to say to pair and to be paired. Okay, so this is where the theoretical work of Danghai Li and Zhixiang Li comes in. And they really did a very serious calculation of the Hamiltonian coupled to the magnetic structure. And in this case, we assume that the magnetic moment, the electron-doped system is commensurate, and the magnetic moment is essentially doping independent. So with that model, and you can now see that depending on the correlation length of the system, you can see when the magnetic correlation length is very large, okay, then you only see the segment. You don't see this ghost Fermi surface. Yeah. But when the correlation length gets shorter, then you begin to see the ghost Fermi surface coming in, and you can actually explain much of the factor. So essentially what happened is the following. In a magnetic order, you have two things, okay? You have amplitude, okay? And you also have the orientation one. In this picture, really the amplitudes give you the magnitude of the gap. Is the orientation of fluctuation that allow you to bring back some of the earlier Fermi surface of what we call the ghost Fermi surface. In that sense, these electrons were trying to do two things by utilizing the 2 degrees of freedom itself. Okay, so I hope to give you a thing. You can see that there's a maximum superconductivity, the pseudo gap, and anti-ferromagnetic hotspot. They all happen at this time. The p-type, the electron-doped system, has the benefit that this hotspot is not at the anti-ferromagnetic zone boundary. Instead, it's going further away. So there's a non-monotonic behavior. Then we can sort of differentiate away from the other features such as the Manhole singularity or the coupling to the B1G phonons and all that. So this, in a sense, is a cleaner system, although the TC is lower in this system. Okay, so again, this all happened at the same time, and that's the first part of my story. And I see I'm running out of time. Maybe I can now jump to the second one, namely the strange gap and the frozen pairs. When you really look at this system, okay, one of the key features between p-type and electron type that the electron type, the long-range magnetic order persists to much higher doping. Okay, and in this, we used to think this is just a mass state and it's a total volume state. Okay. I'm hoping to convince you actually it's much richer and more interesting than you think. So I'm going to start out to saying that there's the hidden things. We know there's a big Mach gap undoped, but as soon as doped, as shown very early on in Peter's thesis work, there's a low line excitation occurs. So I'm going to start with, instead of the Mach picture, with a spin density wave picture from that, okay? If you do a spin density wave picture, you ended up, okay? You ended up in a Fermi surface, look like those pockets here in the Brownian zone scheme or in the anti-ferromagnetic zone scheme. I'm talking about 3 to 13% of doping. So I'm not going to talk about half filling the mass state for now. Okay. Now, this behavior again was seen very early on in Peter's thesis. You can see here. You see the emergence of low-lying states near the antinode. Okay, and in the underdoped system, generically, this is also seen by Carl Shen in his thesis work. There's a gapped system and a small gap in this underdoped regime. Okay, and Carl, of course, compared with the p-type. For now, we are going to only look at the electron type. Another thing about electron-doped system in underdoped regime is 4%, 10%, 16%. There is a resistivity upturn. Okay, it's not going insulating, but it's an upturn. It's a peculiar kind of insulating state in this. Okay, so again, here are some of the recent data by Ben, and you can see this piece of Fermi surface, and again, you can see cut number 1, the nodal region is sort of being gapped, and we are going to focus on cut number 3 near the antinode. You can see this state very close to the Fermi level. Okay, is that really true? But when you examine the antinode region, basically what we're talking about is we have a magnetically reconstructed antiferromagnetic metal. This rare piece should have been a metal. But when the data gets better and you look carefully, in fact, this region at the antinode that stays near the Fermi level, but there is still a gap. Okay. Now you can see that it turns out the gap turning on temperature peculiarly is also consistent with where the resistivity upturn is. Okay, and now you can symmetrize it. You find this gap to particle hole symmetric. And now let me compare with this gap at the antinode, which is this piece of Fermi surface antiferromagnetic, with the one that's near the node. You can see that the ones near the node, if you divide by the Fermi function, you clearly see that one is not particle hole symmetric. Look at the rare data, okay? And that's clearly it's the antiferromagnetic gap. But the gap identified at the antinode actually is particle hole symmetric, okay? Even though the material is insulating. In this case, we believe this is the superconducting gap. Now look at the doping dependence. This behavior goes from 4% all the way to superconducting 15, 17% and become a metal in the north. They behave in this way. And then the question is, okay, you have this piece of Fermi surface. Is that a charge density wave? You see, when you have a Fermi surface nesting like this, the charge density wave is a natural thing. And indeed, it's being seen by Silvernato et al. Okay, there's a charge density wave. It's being interpreted in this way. Okay. However, if you look at charge density wave, as you go to increase the doping, the charge density wave goes to higher gap and higher temperature. Okay, even though they're using the same piece of Fermi surface. Okay, so here's the gap. The red, the black are the data of the about gap. You can see it decreases and smoothly evolve into the D wave superconducting gap, while the charge density wave showing at higher temperature and non-monotonic behavior. So it cannot be the charge density wave. Then I already used up the antiferromagnetism. I cannot use charge density wave. So what's left is there are very few options left. I should say bypassing my colleague Bob Lofgren will say you've discovered a D wave, D density wave of that. But now I'll just take a more mundane saying to say that, in fact, we see the same piece of Fermi surface. There's another gap. And this work really done by Donghai Li, and you can show that this gap should be isotropic. Indeed, we find them to be isotropic, and there's no node in this system. I should also point out, in this case, the S wave should have a node, a D wave should not have a node, okay? Because the Fermi surface already been reconstructed by the antiferromagnetism, so you have sign change once. Therefore, the D wave, if you sign change another time, you won't have a node. I won't go into the detail, but this is where we are now. I hope to give you a sense of these two pieces of recent work. One is the Gossamer Fermi surface, and that tells you something about what's the nature of the pseudogap. Certainly in this case, antiferromagnetism play a very important role, but it also shows how clever the electrons are. We're able to use its 2 degrees of freedom to do these 2 interesting things. The second point of my talk is about this seemingly uninteresting and boring region of the long-range ordered state. Actually, there's a very interesting state hidden there. So I'm going to say below this, there's a pair. And again, I'm going to differentiate that. I think there's rapid change with doping melt away from the Mach physics. And here, the spin density wave will be the better starting point to have an understanding of the physics. Thank you very much for inviting me, and I'll stop here. I know I'm running out of time.
Thank you very much, ZX, for this very, very rich talk. We have some time for some questions.
Okay.
You can raise your hand.
I will stop sharing that.
While waiting for questions, ZX, may I ask for your first part? Do I understand correctly? It's different electrons that are doing the folding from the antiferromagnetic order, and then the ones from that are getting paired into Cooper pairs, or it's the same electrons doing both at the same time? Is there
I think in this picture advanced by Donghai is the same electron, because that's the challenge, right? We only have one band and only one set of electrons. That's the challenge of that. But you have 2 degrees freedom, because you in the magnetic order, you have the temperature, and you also have an orientation. And it's the orientational disorder. That's why it happens when you have short correlation lengths, and that gives you this additional Gossamer state. That certainly is how our interpretations are.
Okay, so it's microscopically coexisting. It's not like a.
Yeah, correct.
I see.